Hey everyone, it's AthenaX. In the last video, I introduced the concept of the best fit line, or linear regression. In this video, we'll derive the most common type of linear regression, called ordinary least squares, using calculus. But before you watch the whole thing, please pause periodically and see if you can arrive at a solution yourself. I make some decisions that will seem arbitrary, just to get to some solution, but in later videos we'll explore these decisions along with other solutions. This video will be more tedious, but it does represent the most common case, and that does set the stage for later videos. The classic setup is the following. You have n xy samples. You think that the data roughly obeys the line equation y equals mx plus b. By roughly, I mean that each y value actually equals mx plus b plus a small unbiased random noise epsilon, which is separate for each sample. I won't strictly define small now, and it's not strictly needed, but it'll help us understand the solution to assume it's small. By unbiased, I mean that on average the noise is 0. To make things easier down the line, I will replace m and b with beta 1 and beta 0. So we have yi equals beta 1 xi plus beta 0 plus epsilon I. So for example, if you had the following line, then when you pick some sample x1, then beta 1 x1 plus beta 0 would be on the line, right here. And you add the small noise epsilon I, or epsilon 1 here, to get some y value near the line, maybe here. This would be one data sample, x1, y1. Let's say you get some data that looks like this. You can tell that the true line probably looks something like this. Let's try and quantify this feeling. Pause and see if you can come up with an answer. Ready? So you may have the intuition that the closer the line is to the points, the better the fit. We have the exact x values, and we would have the exact y values if it weren't for noise. So the noise is what puts these points away from the line. Since the noise is small, we'd expect the points to lie near, but not exactly on the line. So these vertical differences, also called the residuals, are the noises. So a line fits the data well if the residual distances are small. Let's add some notation here. Let's say y hat is what y would be without the noise. Now let's say Ri is the residual for the ith sample. So Ri equals yi minus y hat I. Then we plug in the equation for y hat and simplify. Perhaps the best fit line is the line that minimizes the residual distances. But which residual do we minimize? We can minimize the average of the residual distances. This average can be written as 1 over n times the sum from I equals 1 to n of the absolute value of Ri. Pause and think about why we need the absolute value. Ready? We want to minimize the residual distances. It's not that positive residuals are bad, while negative residuals are good. Really, all deviations are bad, and we want to minimize them regardless of direction. If we tried to minimize this without the absolute value, you could actually get an infinitely negative answer. You'd put the line up infinitely high up, which makes the residuals infinitely negative, which would minimize this sum. But that's not what we want. We want to penalize negative and positive residuals. Now we plug in our definition of Ri to get the following. Okay, so what we have so far is actually a reasonable metric to try to minimize. But I'm going to choose a different one. Instead of the absolute values of the residuals, we're going to use the squares of the residuals. For now, this is just an arbitrary choice, but we'll explain it in later videos. The important thing is that whether you take the absolute value or the square, both end up making it positive. It's just that the square will punish further points extra harshly. This approach is called ordinary least squares. This quantity that we want to minimize is called the loss. It's basically the badness score or the lack of fitness score for a given line. And it's a function of beta 0 and beta 1, not of the x's and y's. We're not optimizing the points, we're optimizing our guess of the parameters beta 0 and beta 1. I'll write the loss function as L of beta 0, beta 1. So at this point, unfortunately, we follow the tedious standard calculus-based optimization technique. Since L is differentiable, we find where the derivatives are 0 and confirm that it's a minimum using the second derivative test. If you've only done single variable calculus, it's similar with two variables, so you can still follow along. Please pause and try this yourself. First, let's find the derivatives and set them to 0. dl d beta 0 is the derivative of this, and we can push the derivative inside the sum. So we get this. Now we use the chain rule to get this. And set it equal to 0. Now we'll simplify. We multiply by negative n over 2, and we get this. We'll split this up into 3 sums and factor out the betas. The last term here is just n, so I'll replace that with n. If we solve for beta 0, we get beta 0 equals this. To make this easier to understand, let's define some shorthand. Let x bar be the average of x, so it's the sum of the xi divided by n. Y bar is the average of y. Now we can cleanly rewrite our equation for beta 0 as beta 0 equals y bar minus beta 1 x bar. In other words, y bar equals beta 1 x bar plus beta 0. This is just a linear equation. Specifically, it means the best fit line passes through x bar, y bar, which is the average point, or in other words, the centroid or the center of mass. Now let's calculate dl d beta 1. Okay, so I just copied the loss function, and we're going to now take a derivative with respect to beta 1. Again, we can push the derivative inside the sum. And again, we use the chain rule. And we set it to 0. And just like before, we multiply by negative n over 2, and we're left with this. Let's plug in our expression for beta 0 here in our equation for beta 1. We're going to try to isolate the beta 1. So let's reorder the terms and factor out the beta 1. Now we distribute the xi and split the sum, and again pull out the beta 1. Now you solve for beta 1 and you get this. We could plug this expression back into the expression for beta 0, but it just gives a long formula without much added intuition. So we won't do that. Now, to confirm that these values for beta 0 and beta 1 do indeed give a minimum for the loss function, we have to do the second derivative test, which involves finding the determinant of the Hessian matrix of second derivatives. It's tedious and also doesn't add much intuition, so I won't do it here. But the test does pass, and this is indeed the minimum. If you're familiar with multivariable calculus, I encourage you to pause and try to find the second derivatives and verify for yourself. Cool. Next, let's rewrite beta 1 in a more standard way, which gives a better intuition. First, we'll need a useful identity. The sum from I equals 1 to n of xi minus x bar equals 0. In other words, the deviations from the mean of x to each data point sum to 0. Intuitively, this should make sense. It means that on average, the deviation of a sample from its average is 0. In other words, on average, it's average. But let's prove it. We'll take the left-hand side and show that it equals 0. First, we split the sum. And since x bar is a constant, the second sum is the same as n times x bar. We'll now plug in the definition of x bar. And you'll see that the n's cancel out, and these two sums also cancel each other out, and we're left with 0. By the same logic, we have the equivalent identity for y's. Cool. Now let's apply this to the formula for beta 1. Here's the formula. Using the identities above, these two, we can subtract 0 from both the numerator and denominator of beta 1. We subtract x bar times 0 from the numerator and x bar times 0 from the denominator. So what I'm going to do is beta 1 equals the same numerator minus x bar times 0, where we'll use this definition of 0, over the same denominator minus x bar times this definition of 0. Now we can factor out xi minus x bar in the numerator and in the denominator. So what we get is this. This is how I usually see it written. Those of you familiar with probability may notice that the numerator is basically n times the covariance of x and y, and the denominator is basically n times the variance of x. Well, probability aside, what's the intuition here? If you remember from earlier, we had y bar equals beta 1 x bar plus beta 0. This means the line passes through the mean point, x bar, y bar. What about beta 1? Let's analyze the numerator and denominator. The numerator will tend to be positive when x and y are positively correlated, meaning if the slope truly is positive. Here's an example. Let's say this is x bar, y bar. On the right of x bar, x minus x bar will be positive. Since y generally increases with x, y minus y bar will also be positive. So x minus x bar times y minus y bar is a positive times a positive. So it's a positive. Similarly, on the left, both terms will be negative. xi minus x bar will be negative, and yi minus y bar will be negative. So the product will be positive, and that corresponds to this positive slope. On the other hand, if the line had a negative slope, like this, say this is x bar, y bar, Then on the right side here, xi minus x bar would still be positive, but yi minus y bar would be negative. And similarly on the left side, xi minus x bar would be negative, but yi minus y bar would be positive. So the product would be negative on both sides here, and that corresponds to the negative slope. So the numerator captures the sign of the slope pretty well, but it doesn't capture the magnitude well. The denominator accounts for this. The denominator is a sum of squares, so it's always positive, assuming you have at least two distinct points. So it just scales the numerator based on the spread of the x values. Let's consider an interesting case, changing units. Here's an example data set. The line looks something like this, right? Suppose the x values were measured in meters. What if we had chosen decimeters instead? A decimeter is 1/10 of a meter. So then the points would keep the same y values, but their x values would be stretched by a factor of 10. So you'd get something like this. Now all the points are 10 times further. I'm not going to draw all of them, but you get the idea that they'd be pretty far. This is not drawn to scale. Pause and see if you know what the new slope should be relative to the old slope. And remember, these images aren't drawn to scale. If you want to, you can try drawing something yourself. Ready? It should be 1/10. So the new slope should be 1/10 of the old slope. Why? Well, slope is change in y over change in x. So slope is you go up this much and you go over this much. But if all the x values are 10 times further apart, then for the same amount of y that you go up here, you might go up this much in y, but you have to go all the way out 10 times further, wherever the point might be, to get to the x point. So what does our formula for beta 1 do? Well, the numerator will actually be 10 times larger, but the denominator will be 10 squared or 100 times smaller. So the net effect is that beta 1 will in fact become 10 times smaller. But let's prove this. Let x prime be x if it was scaled by some factor a. Let's assume a is positive. In our example above, a was 10. So x was meters and x prime was decimeters, and there were 10 decimeters per meter. X prime bar is 1 over n times the sum of all the x primes. And if you plug in ax, you get this. So x prime bar is just a times x bar, which makes sense. The mean number of decimeters would just be 10 times the mean number of meters. If we plug this into the formula for beta 1, we get this. So here I'm just replacing the xi and x bar with x prime and x prime bar, which happen to be ax and ax bar. You can see the numerator has this factor of a, and the denominator has a, but it gets squared. So we can actually pull out the a, put it out front, and similarly pull out the a from here, but it becomes squared out front. And then one of these a's and this squared gets cancelled out, gets cancelled out. So you get the same thing as before divided by a. Let's recap. We had a bunch of data, which we assumed came from a relationship yi equals beta 1 xi plus beta 0 plus epsilon I, where epsilon is a small unbiased noise for each sample. We tried to minimize a loss function, which was the average of the squares of the residuals, and in doing so ended up with the following formulas for beta 0 and beta 1. And we massaged the beta 1 formula into a more commonly seen and maybe more clean formula. And we saw how the formulas indicate that the best fit line according to our least squares loss function at least, passes through the mean point, x bar, y bar, and we saw how the numerator and denominator of the formula for beta 1 work together to correct for the spread or scaling or units or however you want to think of it, of x. Hopefully this gives a slightly better understanding of the derivation and intuition of the least squares linear regression. If you have multiple x's and or y's, you can create corresponding matrices, and the second derivative test is more tedious, but it does give the correct answer, and you can find a minimum. We'll cover the matrix version of this in a later video. Until next time.